Hello. There are those who argue that the only successful application of mathematics is to situations in which inanimate objects are involved. They point to Newton's laws of motion as an example of an application that has been a faithful servant over generations. On the other hand, they argue, when the human behaviour is part of the modelling process, then the application is less successful. Ask any Chancellor of the Exchequer how he feels about models of the economy, for example. The area of application that I'm going to talk about is one in which human beings are in competition and sometimes in conflict. You will see some examples of the kinds of problems I address on the transparency. We need, first of all, to get some terminology. So we'll begin by means of a simple illustrative example. Around about the time of an election, an independent poll surveys people's attitudes to the two major parties either cutting taxes or deciding to spend more on social security and the general infrastructure. The results of the survey are shown in this table. For example, if both the Conservatives and Labour agree to cut taxes, then the Conservatives can expect 60% of the poll. Whereas if they maintain their policy of cutting taxes and Labour have decided to spend more on social services as part of their platform, then the vote is halved between the two parties. What should each of the two parties do? Let's look at the figures again. If Labour wanted to cut the Conservatives' share of the vote by picking up 60% and therefore leaving the Conservatives with 40%, they would have to agree to cut taxes. But they then run the risk that the Conservative Party would also cut taxes, and they would actually secure 60% of the vote. If therefore Labour wished to be cautious, then by agreeing as part of their policy to spend more on the social infrastructure, they can restrict the Conservatives to 50% of the vote and hope, perhaps unwisely, that the Conservatives will also agree to spend more. Now, the Conservative Party can read the opinion polls the same as the Labour Party, and they would agree, therefore, that they would not risk themselves only getting 40% of the vote, so they would agree to spend more on social services. And therefore the poll is halved, and that is one way in which that game can be solved. Let's now look at some definitions. We're going to be talking about games, and that was an example of a game, a situation in which two or more players are in competition or conflict. Each player has a number of actions which he can choose to follow or not as the sense of the game dictates. And in those cases, we know the payoffs, what each player can expect to win or lose depending on the combination of those actions chosen. The information is displayed in a payoff matrix, and a player can choose to follow a pure strategy, as we saw in the previous game. On the other hand, it may be that he wishes to pursue a mixed strategy by combining two or more of his actions in some specified combination. Then we need to talk about the value of the game. What is it worth under the best conditions to each player? Now, the game we saw earlier was an example of one in which each player had a well-defined course of action. That won't always be the case. And here is an example of a rather trivial game which illustrates what happens when there is no pure strategy as an optimum. A and B each have a penny coin, and each will choose to display the coin heads or tails. Now, they're going to choose to make the display simultaneously, so that they can't react to what the other person does. And it's been decided that if both coins show heads, or if they both show tails, then player A will pocket both of them. On the other hand, if it turns out that the coins are one head and one tail, then B will pocket both of them. What we can now do is display the payoff to one of those players, and that's displayed in this table here. If both players choose to show the coin as heads, then, as we've said, A would take both of those coins back. But because he already invested one coin in the kitty, his actual gain is +1. On the other hand, if there is a head and a tail, then B takes both coins and A loses the coin he invested, so his winnings are displayed as -1. And the question comes as to what should the players do. It turns out that there is no single course of action which each player should follow to achieve the optimum. No, they must mix the two options in some pattern. But therein lies the danger. Because if A, for example, chooses always to play heads, then B can react by always playing tails, and therefore winning the game. And A has to be much of a numbskull if he can't realise what's going on. If he tries to be slightly more devious and to alternate between heads and tails, again, B could react to that pattern very quickly and still win most games that were played. In these circumstances, then, each player will have to alternate in some unpredictable or random fashion between his two strategies. Let's look at one or two more ideas before we proceed with examples. We have introduced earlier, without mentioning it explicitly, the idea of an equilibrium point or a saddle point. That was the first game we considered, where each player had a single course of action, which, no matter how many times the game were to be played, he would follow. Now, many games don't have this feature, and if we're to solve them successfully, then what we must do is to find an easier method of solving the problem. We hope that one of the strategies will be dominated or dominant, and that the game could therefore be simplified. But we ought to say something about what we mean by a game. The games we'll be considering will have only a finite number of players, and indeed each player will have only a finite number of actions. Now, there are games which do have infinite number of players, an infinite number of actions, but they're not within our purview in this lecture. Furthermore, each player knows which actions are available to his opponents. What he doesn't know is which action each of his opponents will choose. And there's another important thing. We need to know that the players will make their choices simultaneously. They can't react, as I've said before. The gains or losses to each player will be finite. What do we mean by the solution of a game? By the solution of a game, we mean we need to know what the winnings to one player will be, and we need to know the strategies or mixture of strategies that will be adopted. Those two pieces of information constitute the solution to a game. Much of the time, we'll start at the simple end and we'll consider a two-person game. Players will normally be called A and B. Now, what is player A's strategy? Player A acts to ensure that his average gain over a long series of games is at least equal to the value of the game, whatever player B chooses to do. That is not the same as saying that player A tries to win as much as he possibly can. There is an important and a subtle difference. And similarly, we can discuss the situation for player B. We can say that player B acts in such a way that his average loss over a long series of games is no worse than the value of the game, whatever the other player chooses to do. And it's a kind of safety-first approach. Well, as I've mentioned, some games do have a saddle point. And what I want to do is to look at such a game in detail and see how we might effect a solution. Now, here we can see a payoff matrix. A and B each have 3 courses of action. The payoffs to A are shown in the table. And we then start to argue from the point of view of player A. Supposing B were to follow his first strategy, that's the first column, what should he do? Well, he's trying to win as much as he reasonably can within limitations, so his best strategy would be to follow the middle, A2. then he can win 6 items, 6 units, whatever they may be. If B decides to pursue his second strategy, column 2, then again A would follow his second strategy to pick up 8 units. And again in column 3, if B chooses his third strategy, A is advised also to pursue his second. What we've done at the bottom of each column of the matrix is to list the maximum amount that could be won by A if he pursued the right policy, 6, 8 and 7 respectively. On the other hand, if you look at it from player B's point of view, he is trying to limit A's winnings. So if again we go back to the table, we can see that if A follows his first strategy, B can reduce A's winnings to 1, simply by following strategy 3. And if A follows strategy A2, B can restrict the winnings to 6 by playing his first strategy. And if A pursues his third strategy, then A can restrict the winnings to 2, again by playing B1. Let's keep with player B. How can he achieve the optimum for him? Well, he looks at his winnings and says, whatever I'm trying to do, A can't get away with too much. And if he's wise, he can restrict A to winning 6. That's the minimum amount A is guaranteed to win. And he can do that by following his first strategy and restricting A to the 6 units shown in column 1. Given that circumstance, A can also reason similarly and say, well, I can certainly guarantee winning 6 if I play my second strategy. Any other strategy, I might pick up more, but I might end up with less. So they settle on a unique solution, A2, B1. In this case, the maximum of the row minima, 6, is equal to the minimum of the column maxima, 6, and it's the element circled. And that's known as a saddle point. And when you have a saddle point, that method of solution will locate it and tell you which strategies the two players should adopt. On the other hand, not all games have such simple solution, and here's an example of one which doesn't. If you look at the column maxima and the row minima, you can see that the previous method we had of minimum of the maxima and maximum of the minima will not work. Therefore, there is no unique solution. The players must mix one or more of their strategies in some random fashion. Now, if you look at that table, we can see that strategy A2 is not sensible, because A can always do at least as well, if not better, by following his third strategy. We say that A2 is dominated by A3. What about the value of the game? Well, it can't be any less than 0, the smallest number in the matrix, nor can it be higher than 7, the largest number in the matrix. But as to precisely what its value is, we need to simplify the game. What we're able to do is to take out from the game the course of action which A will not pursue, namely A2. And the reduced matrix we see here shows what happens when that game solution is deleted. We now have a matrix which has 2 rows. And if there is no saddle point, the next best thing is to get a matrix either with 2 rows or with 2 columns by deleting one or more of the strategies available to one of the players. With this reduced game, we can begin to argue along the following lines. A is going to have to mix his 2 pure strategies in some random fashion. We don't know quite how yet. But whatever he does, A certainly doesn't want to win less than the value of the game would dictate he should. We can attempt to solve the problem algebraically. If we let here A play the 2 strategies A1 and A3 in the proportions Q to 1 minus Q, where Q is a number between 0 and 1, then he can consider what happens for each of the strategies of B. And when you combine the proportion of times played with the value achieved at that particular play, then if B follows his strategy B1, the combination shown there, 1 plus 3Q, has to be at least equal to the value of the game, and probably larger, if it's to be worthwhile for A. We can repeat the same procedure using entries in the payoff matrix and the fractions q and 1 minus q, and obtain similar values for B2 and B3. The great advantage of having two variables for one player is that we can draw pictures, and that's precisely what we're going to do in order to effect the solution here. The diagram you see shows the three strategies of B plotted on the same axes. The left-hand vertical line is strategy A2, which means Q equals 0, and the right-hand vertical line is the strategy A1, where Q equals 1. And we've plotted on a linear scale the points for B1 at A2 and B1 at A1 and drawn a straight line to connect them, and similarly for the other two strategies of B. Notice that I've said B3 is dominated. It wasn't obvious from the matrix, but it is obvious from the graph, because although it's not dominated by one of the other strategies, it is defeated by their combination. And if you look at the diagram again, you will see that if we're aiming, as B must surely do, to achieve the least value for every possible Q that we can imagine between 0 and 1, then he will stick to the straight lines formed by B1 to the point of intersection with B2 and down again. B3 doesn't get a look in. So there we've discovered graphically that the strategy is dominated. To find the solution of the game, all we have to do is to work out the coordinates of the point of intersection, as we've done here. The solution is where the two straight lines intersect. That is that the value Q is 2/3, which means that A1 should mix his strategies A1 and A3 in the proportions 2/3 to 1/3 and should ignore A2 altogether. And if you substitute Q equals 2/3 in either of the expressions at the top of the transparency, we get the value of the game is equal to 3. And that's the best we can do. We could similarly solve the problem from the point of view of the other player. But rather than look at it as an abstract, let me give you an example in which the same strategy can be employed for the solution. High Street War is what we've called it. Two supermarkets, totally fictitious of course, are in competition. Now they have to decide on a weekly basis what policy to pursue. They have two main methods to try and attract more customers: cut prices or advertise in the local papers. They have to decide this in advance on a weekly basis. So there's no question of reacting to the other supermarket, they must make up their mind at the same time. Now we have certain information which we can quote. When both the supermarkets use the same method, the profit of Makeway increases by £1,000 at the expense of Fresco. So from Fresco's point of view, their net profit has decreased by £1,000. If, on the other hand, Makeway decides on price cutting and Fresco settles for local advertising, then Makeway loses £3,000, which means a gain to Fresco of £3,000. If Fresco goes for price cutting and Makeway goes for advertising, Fresco gains £2,000. We have to decide on the best strategy for each supermarket. So what we've done is to put the information into a matrix or table where we're showing the payoff in thousands of pounds to Fresco for the different combinations of A, local advertising, and P, price cutting. The game doesn't have a saddle point as it's readily determined, and so we have to use a graphical method in order to obtain a solution. And if we produce the graphical solution, then the same procedure as before shows that the average loss to Fresco in the optimum strategy is 5,000 over £7. Not a simple number, but not everything works out as simple numbers, even in these examples. And it advises us that Makeway should advertise 3/7 of the time and should price cut 4/7. The theory of games really had an impetus in the Second World War, and problems of strategic warfare really provided a launchpad for many of the methods we're looking at today. Here's an example of such a problem. That A has 2 aircraft which he's trying to send on a mission, and B has 4 missile batteries to cover 4 possible approaches to a strategic target. Each battery can shoot down with certainty only 1 aircraft on its approach. What should each player do? We can examine the strategies for the two opponents. There are two for A, to send the aircraft on different approaches or to use them on the same approach. And B has 5 options. He can put one battery to cover each of the 4 approaches, or double up and leave 2 of the approaches exposed, or 2 on one, 1 on each of 2 others and leave a 4th exposed, or 3 on one, 1 on another, or all 4 covering 1. The payoff matrix can be worked out after a little bit of arithmetic, not too difficult, but it's tedious. We've done that already. And we can see the payoff matrix here. B would be a fool to consider strategies B4 and B5. Remember, he's trying to keep the scores down. And so B4 or B5 would do worse for him than B3. He therefore ignores those 2 strategies, concentrating simply on his 3 strategies, B1, B2 and B3. That allows us to consider a reduced game, which we've done here, and that reduced game can be solved in much the same way as the previous example. We'll merely quote the solution to you, that A should mix the strategies in the proportions 3/8 to 5/8. B ignores, in fact, his 3rd as well as his 4th and 5th strategies and plays 1 and 2 in the proportions 1/4 to 3/4. So that kind of matrix game is fairly easily solved. There are ways of identifying a saddle point. Should a saddle point fail us, we can look for dominated or dominating strategies and use a graphical approach if we can reduce the options for one player down to only 2. But we've not said anything about the criterion, which is a sort of safety first criterion of trying to minimize the maximum losses and maximize the minimum winnings. The question is that strategy always the right one? And if you look at this table here, you can see that A has 2 options, B has 3. Now, if you apply the matrix methods that we've been looking at earlier, then it says that B does best to ignore strategy 1 and concentrate on strategies 2 and 3, alternating them with equal frequency. And A should alternate his options with equal frequency as well, both on a random basis. But does it make sense? Is it always going to be the way in which such problems are most successfully solved? Consider these questions. Most people, I suspect, would probably be prepared to gamble for £10, perhaps with a chance of 1 in 10 of success, rather than take a certain £1. It's not clear, it would depend on the audience, as to how many would take a certain £10 or gamble for £100 with a 1 in 100 chance of success. But I suspect very few of us would be prepared to gamble for £1,000 at a chance of 1 in 1,000 when there's the option of picking up a certain £100. But you must assume in these games that the players have the same utilities, that they have the same preferences, the same outlooks. Otherwise, they're not competing on equal bases. And that may well be a disadvantage to this kind of approach. That's something that you must consider and weigh up for yourselves. Another class of problem is known as the prisoner's dilemma, and it classically arose in the problem shown here. 2 men are arrested and placed in separate cells. Now, each is told by the interrogating officer that if you both keep quiet, I have enough evidence to put you away for 1 year for carrying offensive weapons. But, of course, that's not the end of the story. If the 2 decide to confess, then they can both be convicted and sentenced for 5 years for a more serious offence. However, should one confess while the other keeps quiet, then the one who's confessed will receive 6 years, will receive no sentence at all for turning Queen's evidence, if you like, whereas the one who has remained silent will get an extra 1 year for not cooperating with the police. Well, what should they do? Most people, I guess, would prefer a sentence of 5 years to a sentence of 6 years, and would prefer to get off scot-free rather than be put away for 1 year. And each person independently, therefore, will come to the conclusion that it's best to confess. Result? they both end up with a sentence of 5 years, whereas had each trusted the other and both had kept quiet, they could have got off with a sentence of 1 year. But it's the fear, isn't it, that you can't trust the other person. And the other person having a sentence 6 years less than you doesn't appeal. Now that's a bit artificial, of course, but there are circumstances in which the same problem can be looked at in everyday contexts. And here's one of them. Two firms are trying to sell the same product in a particular area, where the selling price and the total sales are fixed. If one advertises more intensively than the other, the hope is that that person can pick up more of the sales. And what is the result? The result is that both will spend more on advertising in order to try to capture more of the market, but because they're spending the same amount on advertising, then they're ending up with no more of the market, but the net result is that the advertiser has benefited and their net profits go down, because they can't trust the other person. Perhaps more poignant at the moment, when there is a water shortage, is a problem of conserving water supplies. People are urged to save water. Now you and I know that what we do, putting a small amount of water on the garden to make it look pretty, isn't going to really affect the overall situation. It's going to have a minor effect. However, if everybody takes that view, then what happens? Everybody suffers, because the total demand on the water supply has been too much. And at the moment there is the happy sound of people watering their garden under cover of darkness right up and down my street. And it's again the business of not trusting the other person. For the more agriculturally minded, here's a third example. The problem of overproduction. In order to keep prices up, farmers will have to agree voluntarily to limit their output. But each farmer could reason, by him or herself, that it doesn't really matter whether I overproduce or not. My contribution to the total is minuscule. So the net result is each person, being a bit selfish, is tending to overproduce. And the net result is they all suffer. So there is the prisoner's dilemma. I can't trust the other person, so I end up with a less satisfactory situation. Another example we might consider in that context is the problem of nuclear weapons. Here we can see 4 preferences. Each country, and let's just assume there are 2 playing at the moment, has a choice of either keeping or disarming, and the preference table might be this. It's better to have weapons when the other person doesn't. That is preferable to neither having the weapons, which is preferable to both having them. It's a more unstable situation. And worst of all is having your opponent armed and you unarmed. What do you do? Well, it would be nice to trust the other person, wouldn't it? It would be nice to get rid of the weapons, but you daren't risk option D. So in order to avoid option D, you settle for option C, your third choice, where by cooperation and trust you could achieve a better preference. And it occurs on a less national scale. Whooping cough is a disease which babies are prone to, and a vaccine has been developed which unfortunately runs the problem of a side effect. Here again we can put 4 preferences for a typical parent as compared to the rest of society. And we can see that the choice of whether to vaccinate your child or not, well, if all the children were vaccinated bar yours, there would be little chance of an epidemic, little chance of your child catching the disease, and if it hasn't been vaccinated, no chance of having the side effect. That would be ideal. Next down is every child being vaccinated. Then the chance of an epidemic is small, even though your child runs a small risk of the side effect. Following that, the next preference is that no children are vaccinated, at least everybody's in the same boat, and at least there's no side effect danger. Worst of all is if you're the only one to have your child vaccinated, everybody else doesn't, and your child runs the risk singly of a side effect. Consequently, in order to avoid D, you'll settle for C perhaps, and parents tend not to have their children vaccinated rather than all taking the same risk and going to a higher option. On the wages front, which was another area which gave rise to these problems being studied in more detail, a firm has only enough money to satisfy either 2 low-wage demands or 1 high and 1 low. Now, again, you can get a lot out of the situation if you both make either a low demand or, more preferably, one makes a high demand, one makes a low demand, both demands can be met, and the 2 participants agree to share the difference. However, more likely is that in order to avoid option D, the 2 players will each put in a high demand and they'll end up with nothing. Spite has triumphed over cooperation. Another class of game which has been studied to a reasonable extent is that of the duel. And there are 2 kinds of duel that can be fought between players. One here called a noisy duel. It's been idealized, obviously, for simplification of treatment. 2 men are standing a certain fixed distance apart, and at the same time they walk towards each other 1 pace at a time. Each has the opportunity to fire or not, and then the game continues for the next step forward. The disadvantage in going early is that if one player decides to fire, he has to carry on until the second man fires if he's missed. Of course, the temptation is to wait until you're sure of hitting your target. The danger is, if you do, the other person may have fired first and been more successful. Another kind of duel is the silent duel. And here, you don't know that the other person has fired. And an example might be, as shown here, that 2 aeroplanes far apart can fire without knowing that the other plane has already launched its missile. Would this affect your decision when to fire? Well, it can do, and an analysis, which we don't have time to go into, can show that with the same priorities and same chances of hitting at different distances, it does make a difference whether you regard the game as a noisy duel or a silent duel. But the business about cooperating is quite important. And let's go back and look at another example of this kind of situation. We call it a non-zero-sum game. The games with which we started this lecture were zero-sum, insofar as what one player gained, the other player lost. Here we have a situation shown in the table where each player can take something from a common external pool. A has 2 options, the 2 rows, B has 2 options, the 2 columns. The payoffs are shown as a coordinate pair. The first coordinate is the payoff that A would receive, and the second coordinate the payoff that B would receive under the particular combination of pure strategies. Supposing we have no cooperation whatsoever. A sees the first coordinates. Those are his payoffs. And the methods we've considered earlier suggest he mixes 2 options in the row 1/3 to 2/3 proportions. B, on the other hand, sees the second coordinates, and he decides to mix his strategies in the ratio 1/3 to 2/3, and by that each player is able to obtain a profit of 10/3 from the system. But look at those figures again. If they were able to cooperate, they could pick up 15 units between them, not 2 lots of 10/3, which is only just over 7. If you look at the table, you will see that either by A playing his second strategy and B playing his first, or vice versa, one player can win 10, the other player can win 5. Now, 15 is better than the combined total on the matrix game. Why don't they cooperate then? Why doesn't one player who gets the 10 agree to share half the difference with the other? Now, if they're both greedy, and again you go back to the table, you will see that A's chance of winning 10 occurs by him playing his first strategy. So if he's greedy, that's what he'll do, all the time. B, being greedy, wants the second coordinate to be 10, and he plays his first strategy all the time as well. So where do we end up? In the top left-hand corner, with the 2 players each gaining nothing. They haven't cooperated, and consequently they haven't won anything. Cooperation would have been so much more successful for them. How these games are solved is shown in the next few transparencies. Here we have another example of a non-zero sum game. The coordinates again refer to the winnings of A in the first case and B in the second. A looks at it from his point of view. He decides that his best option is to mix his two strategies equally as often, and when you go through the solution process you see that A wins a half by that approach. Now we can do the same thing from B's point of view, and a similar table can be displayed. The second coordinates for B this time. His strategies are slightly out of balance. He plays the first one on 1/8 of the occasions the game is entered into, and 7/8 for the second strategy. And he can guarantee that way average winnings of 1.5. So that's without cooperation. That's playing it according to the matrix situation. But what happens if they're prepared to cooperate? Well, we can look at the thing graphically, and here is a game diagram which depicts the situation. We have 4 corners with the coordinates labelled on them, which represent the 4 combinations of pure strategy that were evident in the previous table. They define a region, in this case it happens to be a rectangle, on the boundaries of which or within which lie all the possible solutions to the game. The boundary is called a convex hull, and if you imagine taking a large piece of string and lassoing the 4 vertices and pulling the string tight, then the shape taken up by the rope will be equal to the boundaries of the diagram. And what we have inside and on the boundary are called convex combinations of the vertices. Some of you may be used to linear combination, a number times the first option plus a number times the second. If each number is between 0 and 1, and those two numbers add up to 1, we have what's called a convex combination. An easy example of which is halfway in between, where the two weightings are equal to a half. Along each edge, you get a convex combination of the 2 vertices. In the interior, you get a convex combination of 3 or more vertices. For example, the point marked with the blob in the middle here, you could regard as a convex combination of the top 3 vertices or the bottom 3. There's not a unique representation. Well, what did we say earlier? We said that by himself, acting on the minimax strategy, A could expect to win half. B could expect to win 1.5. And those are called security levels, because without cooperation, you can achieve those targets. With cooperation, you hope to do better. So what we've done on the diagram is to mark those levels in. In the interior of the diagram, starting at A, the vertical line downwards represents half a unit to player A, and the horizontal line, which comes marked B, is the level 1.5. Of the original convex combination of points in the diagram's boundaries or interior, only those which lie to the right of the line A equals a half, or above the line B equals 1.5, need to be considered. And that forms a small triangle in the right of the diagram. And if you look at that small triangle, the points contained in here represent the only solutions that are feasible, that is even worth considering any of those solutions by cooperation. But I put it to you that not all of those are worth considering either. In that triangle, the only points worth considering are those on the diagonal AB. Why? Because if you're in the interior of that triangle, you can always move in a general northeasterly direction, which means that A does better and B does better as well. And surely that's common sense for both players. But once you get on that line connecting the points A and B, then if you move from whichever point you currently are situated, either you move downwards and to the right, in which case A does better and B does worse, or you move up and to the left, in which case A does worse and B does better. It's impossible at any point on that line for both players to improve simultaneously. And that is what we call a negotiating set, and represents in the context of the problem the area in which the arguing and the debating will take place. Well, that's an example of the whole area of bargaining, which is a topic on which many books have been written and much debate takes place. There are complications, of course, and here's an example of one such complication. B has got two strategies. A has only got one. B will pick up a winning of 1 unit by playing his second strategy and won't win anything at all by playing his first. A will win £1,000 if B follows strategy 2 and will only win 100 if he follows strategy 1. Well, B would obviously prefer 1 to nothing, so he may well offer A the option that if you make it worth my while, I'll play strategy 2, but if you don't, I'll play strategy 1 as a threat. Perhaps the difference to B between 0 and 1 is negligible, in which case it doesn't matter, and he's got a real lever on which to bargain against A. Of course, on the other hand, it may not be so. It depends on financial circumstances, and it may be that B would be desperate to add 1 unit, however paltry, and his threat wouldn't be so plausible. Again, another example. Each time, A and B have a choice. Now, B could threaten to play his first strategy out of spite, if you like, in order to try and force A to play his second strategy. £1,000 to B is well worth winning, and he can only get that if A plays his second strategy. Of course, A is going to lose. Had B chosen to play strategy 2 and A plays strategy 1, A could pick up £1,000 or 1,000 units. But is he prepared to throw all that away rather than lose from 1,000 to 900 by agreeing? The chances are A will probably agree, but again it depends on particular financial circumstances. In this example, we can see a similar situation, but the figures are slightly different. Now B's threat appears less plausible, because the difference between 800 and 850 isn't that much, any more really than the difference between 1,000 and 900. So B's threat now appears less plausible, and it depends on a spite factor as to whether he's prepared to carry it out. One area which has attracted a lot of work and attention is that of politics looked at mathematically. Well, here's a very simple view of what's on offer. 3 voters have to consider a particular piece of legislation, O, the original bill, or an amended version, A, or want rejection of both, N. And you see there the first preferences of each of the participants. Supposing the procedure were that the original bill is put up. Either it is accepted, in which case it becomes the legislation, or it's defeated, in which case the vote proceeds as to whether the amended version should be taken or the bill should be rejected in toto. Now, supposing we have the first vote then. A is going to vote for, because that's his obvious preference. B and C vote against because it's not their first preference. Then the vote on whether the amended version or total rejection should be taking place, and C is the only one to vote against, because A, if he can't get the original bill, would prefer the amended bill, at least under the assumption of the preferences shown at the bottom of the transparency. And by sincere voting, I mean that they vote strictly according to those preferences. So if the procedure were original against other options, and then if the original fails, amended version against total rejection, we've seen what happens. But supposing now the procedure was slightly different. Supposing it were here, that the amended version is put up first of all, which is quite traditional, and if that's passed, it becomes the legislation. If it isn't passed, then we have to choose between the original and no rejection. Well, on the first vote, B is the only one who wants the amended version. A still wants the original. And so, away we go, and the vote is defeated. Then we vote as to the original opposed to no bill at all, and you have 2 votes in favour and 1 against. So, the original bill. Different result, because the voting strategies were different, even though the participants had the same preferences. On the other hand, if C chooses to be awkward, he can actually get something different. He can vote for the amended version at the first stage, and that will be carried. Now, will the other players allow this? Well, as I've said, a lot of work has gone into considering these strategies of voting. I ought to conclude by considering one type of game which most of us experience to a greater or lesser extent in our own lives, and that is a game in which the other player is Mother Nature. Consider the two examples that we will see. First of all, this one. Do we hold a charity fundraising event? Yes or no? Well, we have to worry about the weather. We believe that there's a 70% chance that the weather will be dry and a 30% chance that it will be wet. If we don't hold the event, we incur no losses. That's simple. If we hold the event and it's wet, we can expect to lose £200. If, on the other hand, we hold the event and it's dry, we make a profit of 100, which is a negative loss in that sense. What should we do? Well, let's have a look at another example before making up our minds. It's one concerned with insurance. Do you take out insurance or don't you? Let's look at these figures. You could have an accident, or you might get away with it. If you're not insured and you don't have an accident, it doesn't cost you anything. If you do have an accident and you're not insured, it could cost you £10,000. If you're insured, you could cut that loss down to £4,000. But if you do take out insurance and you don't have an accident, you've spent £100 on the premium, which hasn't been utilised. And there you have the chance of an accident occurring or not. Now, what do you do? Well, that depends on your criteria. You could bring those probabilities, those chances into account and say, what's the average loss I could expect by following one action or another? And then you could go for whichever action on your part gave you the lower average loss. Yes, you could. But would you? Most of us would play the pessimistic game and would actually take out insurance even though there were just a small risk of the accident occurring, because we daren't face the risk of that full £10,000 if we weren't covered. Well, what I've tried to do in this talk is to take a little view at the whole vast area of the theory of games. In the time available, all I've been able to do is take you to the shop window and show you some of the goods that are on offer inside the shop. My hope is that some of you will be sufficiently interested to want to go into the shop and to browse around and perhaps make a purchase. Thank you.